thank you. We're going to go ahead and let Christopher kind of give the introduction, and then I'll cover the meat of that talk. So, Christopher.
Thanks. Yeah. So we're going to talk about Hyperlaunch, a project that we've been working on with Starlab for a little while now, and this is a description of what's happening and where we're going with it. So just a quick introduction to Daniel and I. Daniel is the recently appointed maintainer of the Xen Security Modules for Xen, consultant to Starlab, working on Hyperlaunch and advanced projects. Has been an OpenXT contributor since 2014 and launched the Trench Boot project in 2018. I work with Daniel. My name is Christopher, and I'm the maintainer for the Argo inter-domain communication transport for Xen. I'm also a consultant to Starlab for Hyperlaunch and advanced projects, and I've been an OpenXT contributor since 2016 and a Xen contributor for a little longer. Next slide, please, Daniel. So, for those of you who may or may not be familiar with Starlab, I just want to give a quick intro to our sponsor who's funded Daniel and I to pursue this. Starlab is one of the sponsors of the conference and has been a leader in technology protection space for aerospace and defense customers. Their team specializes in embedded development, including work with open source technologies such as Xen on x86 systems with Yocto. They also do cyber protection, anti-tamper technology, applied cryptography, AI, and anti-exploitation. And their new product, Cyber Hardening Suite, operates on the premise that the attacker is already there. So it's rather security focused, and hence Xen and a Type 1 hypervisor is of keen interest. So, how did Hyperlaunch come to pass? So I just want to give a quick talk about the motivation and background for Hyperlaunch. It's a project that is changing the way that a Xen system starts. We're doing this work upstream in the Xen project hypervisor, adding configurability and flexibility to start virtual machines during system launch. And this work is inspired by previous work with Xen on system disaggregation, which we'd like to reference and acknowledge here. So the first one on this list is Xor, a peer-reviewed published academic research paper entitled "Breaking Up is Hard to Do." This is about inserting separation in between components in an existing fully capable virtualized system in pursuit of hardening the trusted computing base via new, narrower interfaces between components to improve protection for guests from one another. So this paper was exploring separation of pieces, their responsibilities, and their life cycles. So moving on from that piece of work, the next is the hardware domain builder from 2014. This was work sent to the Xen mailing list by Daniel de Graaf, the XSM maintainer at the time. And this builds on the Xen hypervisor's separation of hardware domain and control domain. It uses XSM for granular assignment of permissions to domains. It used the initial domain to start multiple domains with separate system functionality between them. And this work is earlier foundation work, so it was more constrained in development scope than the broader, more full-fledged Hyperlaunch work which we're pursuing at the moment. But it is a piece that our work stands on. The next in the list is the Secure Virtual Platform Research from the United States National Security Agency. This work was exploring the use of virtualization to and creating general purpose system architecture with proper distribution of security functionality with flexibility through configuration. And Hyperlaunch aligns with this approach and vision, and it follows its results. The next earlier piece of work would then be Xen Client XT, which was a Citrix product built with the Xen hypervisor, doing desktop client virtualization. It was subsequently open sourced and released publicly as OpenXT. So this piece of work pursued early adoption of important hardware security features, and included measured launch of the system during host boot using Intel's TXT and VTD, and the IOMMU for device isolation to driver domains. So again, it's system disaggregation. And I was involved in building this and the release manager for that project. So to come back to Starlab's interest in Hyperlaunch, it's motivated by redistribution of the initial domains, as in DOM zeros, responsibilities at system boot. And we're pursuing this as part of enabling the use of Xen for new use cases not achievable with other hypervisors. Okay, so we've been working on Hyperlaunch for a little while now. This is the sequence over the last few years that have led to where Hyperlaunch is currently. You can see in 2014 was when the earlier domain builder I previously mentioned was published. In 2018, some members of the OpenXT community worked on the RFC document for what we called DOM-B at the time, short for boot domain. The earliest sort of earlier vision for what became Hyperlaunch. So that generated feedback and comments, and it enabled us to have discussions with the members of the Xen on ARM community who were working on a similar technology which became DOM zeroless and in 2019, which again was about starting multiple virtual machines as the host is launching, but targeting a slightly different set of use cases. The pursuit of low latency start of multiple domains was a critical thing in that community at that time, and it was slightly different than the focus we had for DOM-B, which was more targeting measurement and verification of components during launch. But there's a lot of commonality between the two approaches, which is where in 2020, working with Starlab, we built the prototype for DOM-B, and following on from what we learned from building that, we began pursuing a public design and review and engagement with the upstream Xen community, aiming to deliver this work into the core Xen hypervisor rather than having to carry a fork downstream, which involved making sure that we were addressing the different needs of the different use cases for this type of technology. So that was the bulk of 2021, working on making sure we were incorporating the right design feedback, included switching over to using device tree for the configuration format, which is a bit of a new arrival for x86. It's much more common on ARM. And then in 2022, we have published the first series of the Hyperlaunch code for review. So the RFC was posted at the beginning of 2022, and the more recent full series implementing the launch of PV guests was posted in July, and has had feedback on the list. So thank you for that. And over to Daniel.
All right, thank you, Christopher. So what makes Hyperlaunch? So what I'm going to do is I'm going to step through effectively the 6 steps that you can kind of see in the PV series. Mainly, first we looked at generalizing what the boot info looked like for x86, then moved into adopting that. Once we started to get that adopted in the upper echelon of the hypervisor, we then converted the entry points. That would bring us to then being able to introduce the Hyperlaunch domain builder, so we could do DOM0 and then expand it for multiple domains, and then making the configuration information. So those are the 6 major steps that the series attempted to do. So in the first step, we introduced generalized boot info. And to get an understanding of that, you need to take a step back and look at what the existing x86 boot infrastructures look like within the hypervisor. So in order to configure DOM0 during launch, all the configuration was either by convention or through command line parameters. And as a result, a lot of that information was stored into globals. A lot of it was in central areas, but some of those configuration variables got stored throughout the code base. And then obviously there was the convention side of it, of which boot module contained the kernel, which ones would contain the RAM disk for the system. There was no real centralization of the boot info to make it easy to, when you're with Hyperlaunch, when we get the fixed configuration and bringing it into this. So we realized early on that we needed to centralize this. So the first thing we did was we went and looked at what DOM0 list had already accomplished. So again, since we were going to use device tree like they, as recommended as they were doing, you could see how they started to centralize all the boot info into a central set of structures. One of the aspects that they did in that, from my reading of the code, was that instead of parsing everything, they took an approach of parse as needed, and built up some of these structures as they were going along the construction path. It has the benefit of reducing memory footprint, but increasing time, because every time you go to look up a new entry within the device tree, that you have to walk the device tree, find the offsets, and then pull the values, as opposed to just walking it the one time. So what we did was we actually decided to take the DOM0 list structures and just kind of centralize them a little bit further. So that's where we got to this generalized boot info structure that we constructed here. Now there's a part here that's shaded out that will get expanded as we get into the domain builder. But the idea behind these structures as we constructed them was to provide a central collection of a well-structured information from the boot material that could be used by the domain builder, and then be able to pass on post construction for any late configuration that needed to be done. So once we had the generalized int structures laid out and worked through, the next part was to actually look at how we could generalize the boot info into the core, to adopt that generalized boot info into the core startup. So in order to do that, the first thing we needed to do was take a look at how Xen boot, what its boot flow looked like. So from an x86 standpoint, one of the core structures that was used was the multi-boot 1 boot module structures. Everything would get converted into MB1 structures and then passed into a common point, and which was start Xen. So if you look at it, if you take a step back and look at it as it's being shown in the diagram, you can kind of see that the start Xen is now this demarcation point where the transition occurs. And then we leveraged that so that a way we could actually split this part of the change into two and across multiple patches, so that a way it wasn't one large change. So the first part we wanted to do was adopt these structures in the upper half of the hypervisor, so after start Xen. So we introduced an intermediate translation function to convert MB1 into the new Hyperlaunch structures. And then that could then be filtered through the rest of Xen startup to use the new structures. So I kind of already touched on this. So yeah, as I said, we've got start Xen. We use that to do the transformation and then carry the information all the way through. So once we had that, then we needed to step back and look at the entry points on, did we want to leave this MB1 to transition in the code or not? And the decision was no, we want to unify this all the way through, so that way we don't have multiple different structurings of the boot information. So we also pushed down into the entry points to try to get all of the entry points converted over to, instead of constructing MB1 structures, construct the new boot domain structures, or the Hyperlaunch structures. And so as we go back and look at this slide again, we see that, as I said, we had this temporary conversion point that was dropped in the start Xen. Now we can actually drop that, and then we can start working on changing all of the entry points here to start constructing the new Hyperlaunch structures. And it was, as we said, it allowed us to break up the patch series, so that way now, especially these lower echelon parts, the early parts of this code, it makes it a lot easier for those to be reviewed separate from all of the changes that has to happen in the upper echelons of the startup. So once we had the conversion done, we were now able to start converting the actual domain construction logic that's existent in the hypervisor already for DOM0. So this is where we started to introduce the second half of the Hyperlaunch structures, which is to carry in a well-ordered and well-structured manner the information needed for constructing the domains. And then as we did this, we also went through and started to refactor a lot of the domain construction logic for DOM0 to generalize it and streamline it into effectively the Hyperlaunch domain builder. And as part of this, they also introduced a whole new device tree parser to take in this Hyperlaunch configuration and use it to actually control how DOM0 was constructed versus having to use the command line options. So once we had DOM0 converted over, we were moving on to expanding the domain builder so we could do multiple domains. Now we're finally getting to the point of what we were trying to do with Hyperlaunch. We had to do a lot of work to get us to this point. So once we're here, now we have a generalized domain builder that we built to build PV domains for DOM0. And then we could just take that and start adding the ability to start constructing multiple domains during the launch sequence, iterating through them. We ran into a few challenges in this, obviously, some of which kind of trickles into the next part of this, and is that PV is very reliant on Xenstore. So we had to work through a lot of that as we were working through the multiple domain construction. But at the end, when we were done with this part of the series, we were actually able to construct multiple domains and have them started as part of the boot. Then we ran into the post-construction issues with domain configuration. So PV domains and Xenstore. PV domains are very reliant on having Xenstore to be able to become usable within a system. You can unpause the domain and it'll run fine without actually being able to talk to Xenstore, but you won't be able to connect to its console. You won't be able to control any of its configuration, CPU, memory management, all of that, memory ballooning, memory sizing, all of that was managed through Xenstore, and the Linux kernel is expecting to be able to talk to Xenstore to get that information. Otherwise, it just runs with what it was given when it was constructed. So this is where we kind of ran into an issue, because in the traditional tool stack, this tool stack would construct the memory and it knew where it put certain allocations, specifically for the Xenstore page and the console page. And so therefore it could then turn around and publish that information into Xenstore, so Xenstore would know how to talk to the domain, and the domain could then talk back. Well, we did the issue here is that the Xenstore is not running, so you can't announce those pages to Xenstore when the domains were constructed, because they were constructed by the hypervisor. So the hypervisor is the one that has that page, the page info, and there needed to be a way to convey that information down to the effectively, we still have DOM0 in this place, but whatever the domain is that's running Xenstore, so that the information can get populated into Xenstore. So we looked to, based on the design feedback that we had during the early design phase, we decided to go ahead and move forward with using HypFS. So HypFS allows us to construct this static tree of information that can be read by privileged domains to obtain the information. So we then pushed that, we added the ability to the domain builder to actually construct a HyperFS tree containing all the relevant build information about the domains it constructed. This allows the privileged domains to be able to know what domains were constructed, where their Xenstore pages were, where the console pages are, and able to then do an introduction to a Xenstore introduction for the domain, so that Xenstore can discover the domains and then begin communicating with them. So that kind of concludes what we actually built. So that leads us to where are we going next with it? And I'll leave it to Christopher to walk over this section.
Thanks. Okay, so we've got construction and launch of multiple PV domains as system boot, and we would like to extend this to construct alternative types of domains, so PVH initially, but also subsequently HVM, in order to be able to launch VMs where those are more appropriate execution models. And in addition to that, the focus has been on enabling this dynamic configuration based on what you pass in. But once you're up and running, you're running a sort of traditional flexible Xen system where you can add and remove VMs at runtime as you typically would. But we know that there are also use cases for much more of a static partitioning hypervisor. I think the DOM0-less use cases fit with that, but there's also interest for doing this with x86. And it's interesting. We'd like to do this and have this capability with the same Xen hypervisor binary, so that it's the way that you use it is dictated by the configuration and optionally the XSM policy that you supply with it. So that's one future area of focus for us. So there's an interest in enabling PCI pass-through to those PVH and HVM guests, which means we'll have to look at exactly how to enable that and what the implications are for making sure that the entries going to Xenstore on the tool stack is cognizant. Okay, so I think that covers that one. We're interested in making sure that the stuff that we build integrates correctly with DOM zeroless, so that common functionality ends up in the common areas of code rather than Arch specific stuff, and making sure that we build in a way that supports the existing DOM zeroless use cases, but really we're aiming to have this be built as a single common piece of code rather than have two separate areas of functionality. So some specifics of how to make that work in domain construction, but it looks eminently feasible. We don't see any particular obstacles to pursuing this approach. And we will be engaging with the working group to make sure that we communicate what we're doing before we go and build stuff. Okay, and then to go back to part of the original design work for what was DOM-B, we'd like to build into the Hyperlaunch system the support for the boot domain, which enables supplying a domain that can then sequence the bring up of the other domains that you launch as the system boots, to give you that control and flexibility, and it be configured by providing this boot domain, which is logic outside of the hypervisor, so that the same common hypervisor can be used in very flexible ways by putting this functionality into the boot domain rather than hard coding it into the hypervisor. So there's some we're expecting to be doing some design work on this again, revisiting it after all of the things that we've learned in building the other aspects of Hyperlaunch before we go back to this. Thanks for listening. Does anybody have questions for us?
Jan?
Yeah, there was a mention of not only PVH but also HVM is to be created, which is still a little interesting without mentioning what the plans are towards QEMU. Where would QEMU run in that environment?
Yeah, so the question was, Jan found it interesting that there was a description of not only PVH but HVM guests. And Jan wonders what would happen, where would QEMU run in that kind of environment?
So yeah, that. Oh, sorry, Christopher. Did you want to answer?
No, go right ahead. You're fine.
Okay. So yeah, that's one of the more interesting cases, right? So one of the purposes of DOM-B was to help handle that kind of transition, right? Where you need to be able to have, say, for instance, a stub domain, a QEMU stub domain, and have that stub domain sequence to be started before the its guest is. So in the patch series, there is some preliminary work to allow prioritizing certain types of domains to be started before others, or at least constructed before others, and then ideally the boot domain could unpause them before they unpaused, or got all the wiring set up so that they could be unpaused before the actual HVM guest was started. So that's why PVH will be the first one. That's why a lot of the details on the side was focused on PVH, because PVH will be the easier case to deal with. Once we get PVH working, then we can actually transition into dealing with HVM. Does that answer the question? Or Christopher, do you think you can add to that?
Yeah. I was going to say, I wouldn't preclude, the more in addition to the subdomain model, the traditional DOM0 model, where you have QEMU inside a DOM0, I think it would be possible to enable that structure as well. But it might be interesting to try and actually make it work.
Yeah, obviously correct. So in a DOM0 model, I blew past that one. So yeah, and if you want to do a traditional DOM0 model with QEMU instances running in DOM0, that is where like the information in HyperFast would come in, right? That the information that if you were to do a classic DOM0 construction, all that HyperFast information would fall in there, and as the system's being what do you want to say, finalized, it could basically make sure that things are wired up appropriately. But yeah, as Christopher says, that it's definitely feasible. We just have to work through it. Any other questions?
Yes.
Yeah, you may have covered it, but I didn't realize that you were covering it. But I just want to clarify. You say that with this redistribution of the initial domain, we turn to new use cases. I didn't quite understand what that new use case would be.
So you said that the redistribution of the first of the initial domain would create some new use cases, and he didn't quite understand what those use cases would be. Sorry, hello, we can't hear anybody.
Yeah, sorry. Christopher, do you want to go first?
So one of the early use cases that were motivated by when we were designing DOM-B originally was the structure of virtual TPMs, so that you have the physical TPM isolated, and DOM0 is not given access or control over it at any point during system launch, and you have virtual TPM. You're able to build virtual TPMs for each guest that don't need to have a trust relationship with DOM0, and they can communicate with the VTPM manager domain. So that's a system structure. I think I think that's possibly even mentioned back in the early. Well, I think it's mentioned in the secure virtual platform stuff. But there, I mean, the low latency boot use cases. Talking to the DOM0 list guys is interesting. There's some scenarios where DOM-U is the primary thing you care about, and getting that thing up and running quickly. But for example, having isolated devices in driver domains. There's basically different system structure you can build once you have these capabilities, and by designing it with the boot domain, you're able to have a very general purpose hypervisor, but very configurable, because you can supply a virtual machine that does the connections between and sequencing the startup of the different pieces that you need.
Yeah, and to just add to that, so this is why we highlight the work at the beginning, right? The ZOR paper as well as SVP, and these things is because when you have something like XSM where you can finally assign what privileges each domain has, and you can distribute them in any way you want, you can now take all the privileges that you have in DOM0, and you can, in theory, separate each privilege into a separate domain, give that domain the privilege via XSM, and have it all constructed at boot time, to ensure that no one system had to have all privileges to get the system running.
Okay, yeah, we have a thumbs up from the questioner. Any other questions? Great. Let's thank our speakers.
All right. Thank you, everybody.